Hi everybody, I'm Quinn,
And I'm Will.
and we're going to be doing our video on section 4.4, Real Refrigerators. So, the book really aims to emphasize that we're talking about the reverse of the Rankine cycle, which was covered in one of the previous sections about real heat engines. And it's basically the steam engine is the Rankine cycle. In this case, though, we're using a refrigerant which has a much lower boiling point than something like water used in the Rankine cycle. Alright, so we're going to start by going over some of the key aspects about the PV diagram that we have here on the screen. Specifically, I'm going to take us through each point along the PV diagram and discuss what happens to our refrigerant at each of these places. So, to start off, at step 1, down here, we're dealing with a refrigerant that's a gas because it's on this dashed line indicating that it's within the gaseous region. So, as a gas, it's compressed adiabatically, hence this curve which is called an adiabat. And that means that there's no transfer of particles or heat. So this usually occurs pretty quickly, and this raises the temperature and the pressure of the gas, hence the word compressor here next to this transition from 1 to 2. Alright, now once we're up at point 2, the hot gaseous refrigerant is then passed through a network of coils in contact with the hot reservoir, which exists somewhere up here where the mouse is. So, or indicated over here by this other diagram to the left where it says hot reservoir. So, because it passes through a network of coils in contact with the hot reservoir, it loses its heat and condenses back into a liquid, hence condenser. And you can notice that it's traversing these dashed lines going from a gas back to a liquid phase. And this all happens at constant pressure. Okay, now that we're over at point 3, this next transition is the one that really differs from the Rankine cycle, and this one is much more specific to refrigeration, and it has to do with throttling, which we'll talk about more later in the video. But at this point, the high pressure liquid is passed through a throttling valve, which the book tells us to think of essentially a semi-permeable membrane where one end of a piston pushes particles through, and then at the other side of the membrane a piston pulls particles through. But like I said, we'll talk about that more later in the video. Alright, then at step 4 we have once again a liquid and a gas, and now it's back at a lower temperature. In fact, it's at a lower temperature than what we want our refrigerator to be at. So for instance, if we wanted our refrigerator to be set at something like 36 degrees Fahrenheit, our refrigerant at this point might be around even as low as 10 degrees Fahrenheit or lower. And remember that it's a gas at room temperature, so for it to be liquid and gas, it's obviously much lower than room temperature. Alright, at this point, in the evaporator, the low temperature, low pressure, low volume liquid gas mixture of the refrigerant absorbs heat from the cold reservoir and becomes a gas again, hence evaporation in the evaporator. And it's absorbing heat from the cold reservoir, or like the inside of your refrigerator. Alright, so it's important to note the coefficient of performance, which I will try and label up here in red, if it lets me. Alright, so the book in each chapter goes into detail about the coefficient of performance, and initially it just says that it's H1. Let's see how good this works. Meaning the enthalpy at point 1 minus H4 all over, sorry, I'll make that more clear here, all over the quantity of H2 minus H3 minus H1 minus H4. But this expression is pretty cumbersome, so after the book goes into more detail about throttling, it actually reduces to something much simpler, which is the coefficient of performance is quantity H1 minus H3 all over H2 minus H1. And these are really important for discussing essentially how efficient or how well your refrigerator performs at taking heat out of the cold reservoir and dumping it into the hot reservoir. Alright, so now we found a better program to use, and I'm going to talk about throttling. So the purpose of throttling, like I said, based on the last PV diagram, if you don't remember you can back up the video a couple seconds, was basically to take our refrigerant from a liquid state at high pressure to a low pressure saturated gas, meaning a combination of liquid and gas, and also decreasing its temperature below the temperature of our cold reservoir so that it can absorb heat from said cold reservoir. Alright, so the book gives us this nifty little diagram here, and it goes into detail about how this cool process actually works. No pun intended. So, basically, you would think that for an ideal gas, because of the conservation of energy, you'd think that the energy that it begins with and the energy that it ends with, it shouldn't increase the temperature or anything of that nature. But this equation right here is what actually, including this term, this potential energy term, is key. So what happens is, when these molecules are really crammed together, they actually encounter an attractive force. And this attractive force is negative, much like gravity. I'm sure it's related to gravity. And so, when these particles actually become at a further distance, the attractive force becomes more negative, meaning that the change in potential energy is actually, it increases. And because of this, to conserve energy, our change in kinetic energy actually has to decrease. And because the kinetic energy is decreasing, what that means is that the temperature will actually decrease, because we all know that kinetic energy is related to temperature. All right. So essentially, after the book discusses a lot of the more details about how specifically the attractive forces become more negative, and that results in a decrease in temperature, then we're finally able to make an important statement that the enthalpy at point 4 in our diagram is actually equal to the enthalpy at point 3. And this is very important because this makes our coefficient of performance much simpler. And I'm going to jump over here and write it. So the coefficient of performance, after we make this adjustment, actually becomes something really nice. Just the enthalpy at point 1. Oh, whoops, that was a mistake. Uh-oh. Okay. That's negative, sorry. H3, H2 minus H1. So our coefficient of performance is just the enthalpy right before our compressor minus the enthalpy right before our throttle over the enthalpy right before the condenser, and minus H1 again. And I'm going to pass it off to Will, and he's going to talk about some of the more advanced and application parts of the chapter.
I want to make one comment on this diagram. This picture that we see here is actually a thought experiment that the author goes through. And the throttling process does not actually involve a piston. It's just a valve, but the pistons represent that there's a high pressure piston on one side, and then there's some sort of permeable membrane, which is our valve, and a lower pressure on the other side.
Yeah, so later in the book they actually display these throttles as something of this nature, and I'll kind of try and draw one here. They have a high pressure here, and then it just kind of like spews out into a low pressure zone. Make that more clear. Alright, We're going to jump over and talk about some of the further applications.
All right, guys. So I'm going to go over the rest of the chapter, essentially. The first thing that I'm going to talk about is the Hampson-Lindh cycle. It has to do with the liquefaction of gases, which is a necessity if we want to get anything really, really cold. So this cycle works for CO2, and it also works for nitrogen. And it will also work for helium or hydrogen, but for those, you're going to have to pre-cool the entire thing because the throttling process will actually heat those up originally. So this diagram, we see over here, we have a compressor. Way over here. And I got the program to work. So we have a compressor, which is pumping the gas. This is where the work is being done. It's flowing through. We have a cool bath right here that it's going through. And it's going through our throttle way over here. At first, the heat exchanger component is not in consideration right now. So the gas is getting throttled, which, as Quinn went over, is cooling the gas. Currently, if the process has just started, there's no liquid. Our end goal is to have this cool liquid condensed down here. So after it's been throttled, it's a colder gas. It travels back through here. This is where the heat exchange happens. So now gas that's traveling towards getting throttled is being cooled by gas that's already been throttled. And it's creating this cycle where it's going to get colder and colder and colder and colder until eventually the gas is liquefying, which is our goal. And at this point that the gas is liquefying, now we have to add in new gas in the compressor stage in order to keep the process working. I want to clarify the phenomena that happens in reference to hydrogen and helium. These gases both have to be pre-cooled by the cool bath to a below room temperature. In the rest of the gases, we can just cool them to room temperature, and this cycle will cool them the rest of the way down till the liquefied state. But with hydrogen and helium, they actually become hotter when throttled starting at room temperature. This is because there's very weak attractive interactions between the molecules at high temperatures. And they still suffer collisions in which there's a large positive potential energy. So when the gas expands, the collisions occur less frequently, so the average potential energy decreases and the average kinetic energy increases. This is opposite from what Quinn described in the throttling process, where kinetic energy decreases and we see a decrease in temperature. So here, for hydrogen and helium, if we don't pre-cool them enough, we will actually see them increase in temperature due to the throttling process. So the book goes over and has a chart of it where there's an inversion temperature. For hydrogen, the maximum inversion temperature is 204 Kelvin, while for helium, it's 43 Kelvin. So helium is obviously ridiculously hard to cool, as it will require you to cool it below the temperature of liquid nitrogen, which is 77 Kelvin, to remind you. So, thus, helium was a difficult task to originally cool. Now that I've talked about cooling liquids through the cooling gases to their liquid phase through the throttling process and the Hampson-Lindh cycle, I'm going to talk about approaching absolute zero Kelvin. We were previously limited by the low temperature of 4.2 Kelvin, which is the temperature of liquid helium. Now, if we want to approach 0 Kelvin, we're going to have to get lower than that. We can easily reach 1 Kelvin by pumping away the vapor from liquid helium boiling at 4.2 Kelvin. This decreases the pressure, which keeps the boiling point going lower and lower. This becomes impractical at 1 Kelvin, so that's where the helium dilution refrigerator comes in. The helium dilution refrigerator is a mixture of two isotopes of helium, helium-3 and helium-4, where helium-3 is the light gray working substance, and helium-4 is the dark gray substance. It does not circulate. Helium-3 circulates. This cools the helium still further through evaporation in the mixing chamber, which is down here. This is where it's the system is coldest. This lets us get into the millikelvin range, which is awesome, and still further, we can go into concepts of magnetic cooling and laser cooling. I'm going to talk about laser cooling in a little more detail than magnetic cooling, but magnetic cooling is based off of taking a substance and putting it in thermal contact with our liquid helium, and then giving it a magnetic field, and then reducing that magnetic field after we insulate it from the reservoir of liquid helium. So it's not allowed to give off, to absorb any heat. Laser cooling, which I think is a really awesome application because it doesn't require this liquid helium in the first place. So it doesn't require you to be already in a super cold temperature range. This allows us to go from any temperature, essentially, and cool a cloud of gas to recently they've been able to reach the nanokelvin ranges. But it can easily reach the millikelvin ranges, just like helium dilution refrigerators can. This concept works based on imagine shining one laser on an atom. If you shine it at exactly the right frequency, it will emit a photon due to the photoelectric effect. This photon has both the energy of the photon but also a momentum. So this momentum can come off in any direction, but the laser is only impacting it and giving it a force in one direction. This creates a net force away from the laser. Now, say we decrease the frequency. This will create a force when an atom is moving towards the laser. It will be phase shifted such that it sees the laser at a higher frequency and will feel a force away from the laser. Now we can see that if we put a laser on each axis, we will constantly be forcing the molecules towards the center and slowing them down in the process, which is cooling them. Now, obviously, these atoms will be able to reach the walls of your chamber. So similar to how we treat plasmas, we would treat these cooled atoms by trapping them using magnetic fields. I think this is an awesome application because it allows us to go from essentially any temperature range to a very low temperature range without all this other necessary freezing equipment such as a helium dilution refrigerator.
Alright guys, thanks for watching, and we'll see you when we turn in our finals.
Thanks guys.